Burris. I'm here to talk to you about hardware and why you might want to switch from hard drives to NVMe drives. Let's try this.
That work? Let me try it. You have to put the,
Is it not selected?
yeah, there we go. Just go over it. Yeah. See.
There we go. Okay, cool. So quick intro. Staff SRE at Sony Interactive Entertainment, also the product owner for our storage team. Been there for about 8 years doing SEP most of that time. Our main product that if you're not familiar with it is PlayStation. We use SEP for backend for a lot of our systems, both for right here. It's a global platform. We have object storage, so we use that for S3. We do it in general format for most all of our services. We also have block storage for a lot of our compute. I explained in the previous talk that we have lots of RBDs, hundreds of thousands of RBDs on some of these clusters. And we both run hard drive and NVMe clusters at this time. So kind of comparing these, question kind of came up for us was why should you move from hard drives to solid state? But we kind of want to look at it a little differently here is not why or if, it's more of a when should you move it, right? So a little refresher on hard drives. I think most people have seen these before. So a lot of moving parts. You can only get about 100 to 150 IOPS depending on the spindle speed. Get roughly about like a 2 millisecond latency on these things. Max capacity right now is about 36 terabytes. There might be some other ones out there, but it's not going too much. Depends on the mechanical reliability of these things. You have the moving head and everything. Obviously, you have these spinning disks, and we affectionately call them spinning rust, right? Then NVMe, we have a lot of different things here. You can get about 400,000 to 1 million amps per drive. You're not in the milliseconds, but in the microseconds range for latency. Read and write. Your max capacity right now depends on what type of NVMe you have. Could be about 16 terabytes, a little bit more, maybe even up to 150 soon. You do need to consider the drive rates per day. We'll cover a little bit more of that in a minute. Something a little different than what you had with hard drives. So for NVMe, you have two main variants. You have QLC drives. And you have 16 charges. You're storing 4 bits per data cell on these. The capacity on QLC would be about 32 terabytes to 150 terabytes, depending on what you can get. Your drive rates per day is roughly about half of TLC. You might have like a 0.5 or maybe even lower in some of them. Whereas TLC, you have H charge levels. Means you store 3 data bits per data cell. Capacity right now is, most drives you can purchase about 8 to 16 terabytes, maybe a little bit higher, depending on what you are able to afford for some of these. But this is kind of the sweet spot that we found. And you have higher drive rates per day. Typically, could be lower than 1, but usually you have 1 to you can even go up to like 3, 10, 30 on some of them. Just depends, but your capacity drops as you keep increasing that. So for the drive rates per day, you also have write amplification. So 1 drive rate per day means that you're writing the entire capacity of the drive at that time. But you can also have write amplification where additional data might be rewritten on that as you're doing garbage collection. This is something that the host isn't enacting, but it's something that the drive itself is doing. So you could be exacerbating that drive rate per day and not even realize it. So kind of want to take you through our journey about how we did NVMe's and where we kind of started with SEP and how our systems look. So this is the journey for us. We start off with machines like this, where it's based like a 1U with 12 3.5-inch hard drives, but we also had basically 4 SSDs, SAS SSDs, breaking these up into 3 CDG groups. So you had a lot more little miniature failure domains inside of each of these. As your SSD might fail, you only use a few of these OSDs at a time that you can remove. It was okay, but this is our first step into this, and we were a little bit more cautious in how we wanted to spread that out. We weren't sure how a failure might happen, or how we might recover from any of this. Later on, we moved to what we kind of call our second generation. We increased the density, right? Still using 3.5-inch hard drives, but we were able to fit 24 of these in there. What we did instead, though, is instead of having so many SSDs, we moved to NVMe. We would have 2 of these in the machine, and we did some different configurations for this, where some of them we put into the 2 NVMe's into a RAID 1, but the capacity wasn't quite as high, that gave us some other challenges there. Some others we split, so we'd have 12 assigned to one NVMe, 12 assigned to the other NVMe. So this is all right, but this also didn't provide say like hot swapping of those SSDs. Still, you'd still have to shut down the machine, so that made it a little bit more difficult for certain cases. And then we moved to recently, last year and a half, to our NVMe solution here. So a 3rd generation has 22 NVMe's, all TLC. And you're going to have an increased cost for a lot of this, but we wanted the performance. We were also worried about like the drive rates per day at the time. We weren't sure how that was going to operate. One nice part about this is instead of having any extra drive for like the DB wall, we just have that directly on the individual NVMe that have the OSD process as well. So for us, that was really nice in that we didn't have to have all the special tooling when replacing drives, replacing journal drives, or DB wall drives. You basically you didn't have to map all of that out and have people understand where those were. Each drive, as it fails, could let it go, and then our automation could basically take that one drive out and replace it. Much easier for us. But as we probably happen with other people too, we're still running all 3 of these generations currently as we try to phase out some of the older ones. So looking at the benefits of NVMe, I'll show you some of the latency numbers here that we've seen. First, we'll start off with hard drive again. This is write latency. This is average across all the OSDs on the particular cluster, and but you can still see like how the variance between these, even though like the average is between 50 to 70 milliseconds on this, it spikes up and it varies quite significantly throughout the 90-day snapshot that I took here. Whereas on NVMe, you'll see that it looks like it's spiky, but it's only like plus or minus 1 millisecond on this, with that one little exception in the middle. So the variance there is a lot smaller and a lot more tolerable with folks. So play a little game here. Let's see if anyone can spot the point in this graph where there was some backfill happening. All right, so this is the hard drive, right? Yeah. Obviously it happened. It was something that happened. I don't know, like a bunch of drives were replaced, a bunch of things were going on at that particular moment, right? Obviously it spiked up. Here we actually did get some errors on that request during that time period. It was pretty brief, but still, it's something we don't want to encounter as well. You can still see it's pretty spiky on the bottom there and all that. And then if we compare that to NVMe, which is actually right here on the bottom this whole time, you can actually see it, right? And there's little dips and things there, but it's pretty flat. I mean, yeah, obviously, with the scale of this graph, it exasperates it. You can't see all the, little bars in the NVMe, but it still kind of shows the difference between these two. Something else with the NVMe. Oh yeah, did you have a question?
Yeah. What's latency on the writes, or what size is the write?
Can you repeat your question?
What is the latency of what? Write latency of which size write?
The size of it, I don't know. This is like an average across all the OSDs together.
It just smells exactly like the red caps. This
Yeah.
So you should just set the drives to rate remote and.
Yeah.
These are stats from OSD's reporting, correct?
Yeah. Oh yeah, one other quick thing, brought this up in the previous talk was, if you're doing this kind of thing and you're having all these OSDs and you have thousands of OSDs on a cluster, and if you're running Prometheus, you may not want to have all that, feeding in directly. You might want to do something like a recording rule, something like that to break that down so that you don't have like cardinality across these. Yeah, NVMe's also have command line tool if you're not familiar with this. Very, very nice to be using. Gives you some interesting data. This right here is just basically pulling out the smart data, right? It's still nice to have it within the command line tool here. This is also coming from an 8 terabyte drive, which was being used in production here. You can see that the data written on this particular one, we've written about twice the capacity of the drive currently. So over the course of the lifetime of this particular one, about 780 days. So even though we went with TLC and we were worried about the drive rates per day, doing the math real quick, we're not hitting that anywhere in that range, right? So I know you did talk Cephalcon about similar things about QLC, but this is just one of those things to show like what real life might look like.
Yeah, 99% of enterprise SSDs never use more than 15% of the rated storage.
Yeah.
And I know of a production multi-tenant MTW deployment with mixed large and small object workload, where the drives need 0.01 drive rates per day. So if a QLC SSD is rated at 0.34 drive rates per day, that's still gonna, you have 50 years, at Cephalcon, you use the firmware to show that with previous workload, the drive would, the 2-generational QLC would still last for 52 years.
Yeah.
So the endurance is really FUD.
Yeah, exactly. And this is something like we didn't realize until we had it in production and we saw it and we actually used it with our workloads. I'm not sure if that's going to be true for everyone's workload. Maybe you have something where you're rewriting all that data all the time.
Well, there was even a certain chassis vendor where I tried to say, they were specing like mixed use 3 drive rate per day SSDs for general workloads.
Yeah.
And I'm like, why are you spending that much money? He's like, oh, we need that because of balancing and scrubs. Balancing is not that much, and scrubs are reads, which don't, it's like that has nothing to do with.
Yep. Yeah. It just kind of shows where, we can go with this. And it also shows, if you prefer like the QLC, if that's cheaper for you, the options are more open. There are some other cool NVMe commands, by the way. I'm not going through all of them, but one of the things is some of the manufacturers actually have latency numbers and all this other stuff. And I think it'd be really cool if more vendors had that available so you could, pull all that up a lot easier. Kind of going to the hardware a little bit more here about how hard drives are changing in the future. There's the EDSS format. Basically, this is the enterprise data center format, right? Real quick, if you're not familiar with it, the 3.5-inch drive size that was meant for desktop, the 2.5-inch was meant for laptop, M.2 was also meant for internal laptop. These are not designed for data centers, right? And for the cooling and the power and all that stuff with their connectors and everything. So this new format came out. It's not new. It's just that the adoption rate is a little slower than maybe some people want. It's being used by a lot of the hyperscalers. So your ability to find this on common machines may be a little more difficult. And then also the drive prices might be a little bit higher because of the format, right? It's not as widely adopted. But you have the E1, the E3, but you also have different sizes for each one of these. You have the M.2 would probably go to the E1.S, so kind of that same smaller shape, but you also have the E1.L, which is super long, and it's going to be for an extra long server. And then you have the U2.3 format would go to the E3.S. One other thing that's also nice about these is it distributes the power and the cooling and all that stuff much better. It will also allow for, as we go from PCIe 5 to beyond, to be able to support these interfaces and actually get the full capabilities of those. So yeah, looking to the future for some of this stuff, there's also ZNS, so namespace, ability for the application to be able to store it in the namespace on the drive itself, reducing the write amplification, being able to support more symmetrical types of writes and everything on those. As Nia brought up, there's Ceph Crimson, which is being rewritten for high-speed drives, just like this, and C-Store, obviously, more symmetrical writes. You can probably ask more people about the details about those things, but these are things that are coming up. And one of the reasons also that we picked NVMe a couple of years ago to move towards it was to be ready for this, so that we wouldn't have to refresh all the hardware necessarily. We could move right into the next generation. So some things to consider maybe on your own journey. If you're thinking about, supporting hard drives moving forward to NVMe as well, is how much overhead and impact is hard drives costing you, right? Is it costing actual client interruptions or, latent requests back to those clients? Do your workloads fit better on TLC or QLC? As we're seeing, like maybe QLC would be fine for a lot of these workloads, right? It could adopt NVMe, improve your operational model. Like I was saying, everything's being self-contained on each drive, having those individual failure domains within a chassis. Also, just how people approach those drives. The drive length or MTTR for those is much longer, as from what we've seen. So the time that you might be spending replacing those drives could be a lot longer. You do need to think about the ROI on these things, right? Again, with the picking either TLC or QLC, if you have operating hard drive based clusters, how much is that really going to break down for you and improve your business now? Yeah. And then, are you ready for the future? That's it. Thank you. Real quick, any other questions? Yeah.
So,
Sure.
what you use all the time. So like the challenge becomes kind of fixed over the orders of magnitude more IOPS than you would ever need. Is that statement true, or do you actually benefit from it?
That's what we see as well. The main thing that we see as a main benefit is like when you're doing backfills or any other recovery type jobs, those happen much faster. They also, don't impact the client in the same way that the hard drive based solutions that we've had at least would impact them. One other thing real quick also is someone asked about power. Yes, NVMe's, if you look on the data sheets, they can take up more power. But from what we've seen is that it spends less time in that power hungry mode compared to the hard drives, which is always kind of going up and down and spinning and doing all this stuff. When we look at a chassis for both machines, with like a 24 drive hard drive to a 22 drive NVMe, they're about the same. So if you kind of look at that average over like the course of a month, it's not much different for us. So I think it's just because the operations don't take as much time and they can be in a lower power state essentially. Oh, yeah, go right ahead.
Does your cluster have a bucket in it that has every PlayStation game ever made that you can share with?
It's version only.
Next week. Go ahead.
can you mention briefly enterprise drives versus data center drives?
So at least for us, like the not counting that EDS that format, right? But enterprise drive will still have that U.2, U.3 format, right? It'll have higher endurance and higher slaves on that particular drive. Whereas the new EDSF format has a whole new connector, right? It's going to be able to move beyond just PCIe 5 and go beyond that. And obviously, it's spreading out everything so you get better power and airflow over that particular drive. And whichever one people go with, that'll be interesting to see where it goes. Some of the numbers from a few years ago don't show that we've progressed to the same point that people were predicting. We'll have to see. Yeah, in the back.
I see we have 4 more minutes, so I'll ask one more question.
Yeah.
With respect to SAP, historically speaking, both from HDD and SSD standpoints, as it was mentioned earlier, right? Like
we have a lot of storage IOPS or like storage performance on the table, so to say, from a server standpoint, whether it is SSDs or NVMe's. I mean, some of it also have led from file store to blue store, trying to exploit the potential of performance settings on the server, right? So from with respect to NVMe, specifically speaking in context of object storage workloads, how do you see with respect to RGW and any formats that can exploit the full potential of the number of drives or even of the server? And perhaps there's a solution architecture question in that standpoint with respect to analytical techniques, like how does that stand out?
Yeah, I would say, just for clarity also, like on our NVMe clusters, we all run dual 100 NICs on those things. It just became easier and, you know, they're going well beyond 100 gig now, right? It's not too bad to have those around. We're not seeing the bottleneck on the NIC, we're not seeing the bottleneck with drives anymore, right? There's other things in this underlying system that are more bottlenecks essentially. And we'd like to get beyond that as well, right? And you know, figure out ways to improve upon that. You know, we've tried different things as well. We even tried, you know, do you double up on the number of OSD processes per NVMe drive? Like, yeah, you can, but it didn't really help, you know, and it just complicated things as well. So yeah, kind of to your point, yeah, there's more that can be done there. But I think we find on most of the cases we've addressed it from the hardware side. And then we just need to probably find other bottlenecks. That's all. Yeah, great.
It seemed like, you know, you said you got errors on the really bad latency spike, but mostly the hard drives were satisfying your needs. So why did you you didn't put up cost charts or anything. So why did you actually switch to the NVMe? Did it just turn out cheaper like now, or?
It was one to prepare for the future. We also were looking for the performance that we were wanting to have, and we were hoping for lower latency and everything like that from those machines. And overall, I mean, we are seeing better performance, obviously, but I'm not sure if all the other pieces lined up where it's you know, magnitude's better, but you know, again, the operational impact was much lower for those.
Very cool. All right. Thank you.
Thank you.